For this reason, many rely on simulations and other synthetic techniques to generate tool-use data, as explored later in this chapter. 366, Chapter 8, Dataset Engineering. Tool-use data might also require special formats. In typical conversation data, the user and AI take turns, with each turn containing one message. However, for tool use, the AI might need to generate multiple messages each turn, with each message sent to a different location. For example, it might send one message to the code interpreter and one message to the user, such as to inform the user what it's doing. To support this, Llama 3 authors, Dubé et al. 2024, designed a multi-message chat format that consists of message headers that specify the source and destination of each message, and special termination tokens to specify where the human and AI turns start. When curating data for applications with conversation interfaces, you need to consider whether you require single-turn data, multi-turn data, or both. Single-turn data helps train a model to respond to individual instructions. Multi-turn data, on the other hand, teaches the model how to solve tasks. Many real-world tasks involve back and forth. For instance, when given a query, a model may need to first clarify the user's intent before addressing the task. After the model's response, the user might provide corrections or additional information for the next step. Single-turn data is simpler and, therefore, easier to obtain. Multi-turn data often requires purpose-built scenarios or more involved interactions to capture. Data curation isn't just about creating new data to help a model learn new behaviors but is also about removing existing data to help a model unlearn bad behaviors. Imagine you work on a chatbot like ChatGPT and you hear user complaints that the chatbot is a bit arrogant, annoying users and wasting their tokens. For example, when a user asks it to verify if a statement is factually correct, the chatbot responds with, "The statement is correct, but its style can be improved to be better." It then continues to produce an unsolicited rewriting of the statement. You investigate and find that in the training data, there are several examples of annotations with unsolicited suggestions. You put in a request to remove these examples from the training data and another request to acquire new examples that demonstrate fact-checking without unsolicited rewriting. Each application might require data of different characteristics. Different training phases also require different data mixes. At a high level, however, data curation follows the three criteria: data quality, data coverage, and data quantity. To give an intuition about these terms, if you think of model training as cooking, the data fed into the model is the ingredients. Data quality is equivalent to the quality of the ingredients. You can't have good food if your ingredients are spoiled. Data coverage is equivalent to having the right mix of ingredients, e.g., you shouldn't have too much or too little sugar. Data quantity is about how many ingredients you should have. Let's explore these terms in detail. Data curation, 367. 3. While I love writing, one of the things I absolutely do not enjoy is trying to condense everyone's opinions into one single definition. IBM defined data quality along 7 dimensions: completeness, uniqueness, validity, timeliness, accuracy, consistency, and fitness for purpose. Wikipedia added accessibility, comparability, credibility, flexibility, and plausibility. Many of these definitions focus on data quality in a broad range of use cases. Here, I want to focus on data quality for fine-tuning. Data quality: a small amount of high-quality data can outperform a large amount of noisy data, e.g., data that is irrelevant or inconsistent. The creators of the E-model family found that 10K carefully crafted instructions are superior to hundreds of thousands of noisy instructions. Young et al., 2024. Similarly, Lima, less is more for alignment, Zhou et al. 2023, shows that a 65B parameter Llama model, fine-tuned with 1,000 carefully curated prompts and respond SES, can produce answers that are either equivalent or strictly preferred to GPT-4 in 43% of cases, as judged by human annotators. However, the downside of having too few data examples is that Lima is not as robust as product-grade models. The Llama 3 team also arrived at the same conclusion. Notably, they found that human-generated data is more prone to errors and inconsistencies, particularly for nuanced safety policies. This led them to develop AI-assisted annotation tools to ensure high data quality. Most people understand the importance of data quality, but what does it mean for data to be high quality? The short answer is that data is considered high quality if it helps you do your job efficiently and reliably. The long answers, however, differ for different people. 3. In general, data can be considered high quality if it has the following 6 characteristics: relevant, aligned with task requirements, consistent, correctly formatted, unique, and compliant. Some specific use cases might have other requirements. Relevant: the training examples should be relevant to the task you're training the model to do. For example, if the task is to answer legal questions today, a legal dataset from the 19th century might not be relevant. However, if the task is about the legal system in the 19th century, this dataset is highly relevant. Aligned with task requirements: the annotation should align with the task's requirements. For example, if the task requires factual consistency, the annotation should be factually correct. If the task requires creativity, the annotation should be creative. If the task demands not just a score but also a justification for that score, the annotation should include both scores and justifications. But if the task demands concise answers, the annotation should be concise. 368 Chapter 8, Dataset Engineering. For one painful bug I still remember is when a float column in my data was wrongly stored as integers, which round these values, leading to perplexing behaviors. 5. While this doesn't refer to the uniqueness of your data, having data that nobody else has can be extremely valuable. I used aligned instead of accurate or correct because, depending on the task, an accurate or correct response might not be what a user wants. Consistent: annotations should be consistent across examples and annotators. If you ask 2 annotators to annotate the same example, their annotation shouldn't be too different. If the task is to score essays from 1 to 5, would 2 essays with the same score be of the same quality? Inconsistent annotations can confuse the model, making it harder for the model to learn. Having a good annotation guideline is essential for having annotations that are both aligned with task requirements and consistent. Correctly formatted: all examples should follow the format expected by the model. Redundant formatting tokens can interfere with the model's learning, and, therefore, they should be removed. For example, if you scrape product reviews from a website, you should remove HTML tags. Beware of trailing white spaces, new lines, inconsistent casing, and numerical formats. For sufficiently unique, this refers to unique examples in your data. 5. In the context of model training, duplications can introduce biases and cause data contamination. I use sufficiently unique because specific use cases can tolerate different levels of duplications. Compliant data should be compliant with all relevant internal and external policies, including laws and regulations. For example, if you're not allowed to use PII data to train your models, your data shouldn't contain any PII data. Before setting out to create data, it's important to think about what each of these characteristics means for you. The techniques discussed in this section aim to produce data with these characteristics. Data coverage: a model's training data should cover the range of problems you expect it to solve. Real-world users often have a wide range of problems, and the way they express those problems can vary significantly. Having data that captures the diverse usage patterns. Data curation: 369. Of your application is key for the model to perform well. Coverage requires sufficient data diversity, which is why many refer to this attribute as data diversity. For example, if some users construct detailed instructions with abundant references while some other users prefer short instructions, your fine-tuning data should include both detailed and short instructions. If user queries typically have typos, you should include examples with typos. If your application works with multiple programming languages, your training data should include the programming languages your users care about. Different applications have different dimensions of diversity. For example, a French to English tool doesn't need language diversity but might benefit from diversity in topics, lengths, and speaking styles. On the other hand, a chatbot that recommends products to global customers doesn't necessarily need domain diversity, but linguistic and cultural diversity will be important. For general-purpose use cases like chatbots, the fine-tuning data should be diverse, representing a wide range of topics and speaking patterns. Ding et al., 2023, believe that the most straightforward way to further improve the performance of chat-long-gauge models is to increase the quality and diversity of data employed in the training process. To develop Nematron, Adler et al. 2024, NVIDIA researchers focused on creating a dataset with task diversity, topic diversity, and instruction diversity, which includes instructions for different output formats, instructions with different output lengths, and instructions for open-ended answers as well as yes or no answers. The data addition dilemma, Shin et al., 2024, demonstrated that in some cases, adding more heterogeneous data can lead to worse performance. Meta shared that Llama 3 doesn't deviate significantly from older Llama versions in terms of model architecture. Llama 3's performance gains are primarily driven by improvements in data quality and diversity as well as by increased training scale. The Llama 3 paper has rich details on data coverage through all three phases of train-ing, pre-training, supervised fine-tuning, and preference fine-tuning. While this chapter focuses on post-training data, it's useful to look at the data mix for the same model across all different training phases to compare and highlight the considerations for each phase. A diversity axis that is consistent in all three phases is domain diversity, though what exactly diverse means differs, as shown in Table 8.1. This table shows only high-level domains and doesn't include finer-grained topics, like geometry, which is a subcategory in math. Post-training data also has different diversity axes not shown in the table, such as the number of tokens, both for context and response, and the number of turns. Llama 3 uses synthetic data for post-training, so another dimension is the ratio of human-generated data to AI-generated data. 370 Chapter 8, Dataset Engineering. Table 8.1. For Llama 3, different training phases have different optimal domain mixes. Pre-training supervised fine-tuning preference fine-tuning general knowledge, English, 50% 52. 66% 81. 99% math and reasoning 25% 21. 19% 5. 89% coding 17% 14. 89% 6. 93% multilingual 8% 3. 1% 5. 19% exam-like X8. 14% X-long context X0. 11% X. It's interesting to note that during pre-training and supervised fine-tuning, the number BR of combined math, reasoning, and code tokens accounts for almost half of the training data. While I don't know exactly what percentage of the internet data is math and code, I believe that it's far below 50%. Llama 3 authors shared that annealing the model on small amounts of high-quality code and math data, training the model using an increasingly smaller learning rate with increasingly more code and math data, can boost the performance of their models on key benchmarks. This confirms a common belief that high-quality code and math data is more effective than natural language text in boosting the model's reasoning capabilities. The percentage of code and math data during preference fine-tuning is much smaller, 82% combined, likely because the goal is to reflect the real distribution of user preferences. This brings up a question: how do we decide on the right data mix? A simple approach is to choose a data mix that accurately reflects the real-world application usage. You can also use experiments to find optimal data mixes. For example, Meta performed scaling law experiments similar to what is discussed in Scaling Extrapolation on page 74. For each candidate data mix, they trained several small models on a data mix and used that to predict the performance of a large model on that mix. The final model mix is the best guess mix derived from the experiment results. To evaluate the impact of data diversity and quality, Zhou et al. 2023 carried out an interesting experiment where they trained a 7B parameter language model on 3 datasets of the same size, 2,000 examples, but with different characteristics. The first is high quality but not diverse. The second is diverse but low quality. The third is both diverse and high quality. Figure 8.1 shows the generation quality of the three resulting models. Data curation, 371. Figure 8.1. A 7B parameter model, fine-tuned on a dataset that is both high quality and diverse, outperforms that same model fine-tuned on a dataset that is either diverse or high quality. Image from Zhou et al. 2023, the image is licensed under CC by 4.0. Data quantity. Asking how much data you need is like asking how much money you need. The answer varies widely from one situation to the next. At one extreme, Jeremy Howard and Jonathan Whitaker did a fun experiment to show that LLMs can learn from a single example. At another extreme, some teams have fine-tuned models with millions of examples. While millions of examples sounds like a lot, it's small compared to the data typically needed to train a foundation model from scratch. For reference, Llama 2 and Llama 3 were trained using 2 trillion and 16 trillion tokens, respectively. If each example is 2,000 tokens, it'd be equivalent to 1 billion and 15 billion examples. 372, Chapter 8, Dataset Engineering. You might wonder, if I have millions of examples, shouldn't I just train a model from scratch? You can and should evaluate whether training a model from scratch would improve your performance. While fine-tuning on top of a pre-trained model is typically more efficient than training from scratch, there are situations when fine-tuning can be worse, especially when you have a lot of training data. This is due to a phenomenon called ossification, where pre-training can ossify, i.e. freeze, the model weights so that they don't adapt as well to the fine-tuning data. Hernandez et al., 2021. Smaller models are more susceptible to ossification than larger models. Other than data quality and data diversity, 3 other factors influence how much data you need. Fine-tuning techniques. Full fine-tuning promises to give the best performance, but it requires orders of magnitude more data than PEFT methods like LoRa. If you have tens of thousands to millions of instruction, response, pairs, you might want to attempt full fine-tuning. If you have only a few hundred or a few thousand examples, PEFT might work best. Task complexity. A simple task, such as classifying whether a product review is positive or negative, will require much less data than a complex task, such as a question-answer ing about financial filings. Base models performance. The closer the base model is to the desirable performance, the fewer examples are needed to get there. Assuming that bigger base models are better, you might need fewer examples to fine-tune big models. This is the opposite of pre-training, where bigger models need more training data. OpenAI's fine-tuning guide shows that if you have fewer examples, 100, more advanced models give you better fine-tuning performance. This is likely because the more advanced models already perform better out of the box. However, after fine-tune ing on a lot of examples, 550,000, all 5 models in the experiment performed similarly, as illustrated in Figure 8.2. Data curation, 373. Figure 8.2. With 100 examples, more advanced models give much better performance after fine-tuning. With 550,000 examples, all models give similar performance after fine-tuning. Experiments done by Stanford Natural Language Inference, SNLI, Corpus. In short, if you have a small amount of data, you might want to use PEFT methods on more advanced models. If you have a large amount of data, use full fine-tuning with smaller models. Before investing in curating a large dataset, you might want to start with a small, well-crafted dataset, e.g., 50 examples, to see if fine-tuning can improve the model. If this small dataset is sufficient to achieve your desirable performance, that's great. Clear improvements suggest that more data will improve the performance even more. If no improvement is observed with small data, a bigger dataset will rarely do the trick. However, be careful before concluding that fine-tuning with a small dataset doesn't improve a model. Many things, other than data, can impact fine-tuning's results, such as the choice of hyperparameters, e.g., the learning rate is too high or too low, data quality, poorly crafted prompts, etc. In the vast majority of cases, you should see improvements after fine-tuning with 50 to 100 examples. 374, Chapter 8, Dataset Engineering. 6. In designing machine learning systems, I also covered other techniques to reduce the demand for annotated data, including weak supervision, semi-supervision, and active learning. It's possible to reduce the amount of high-quality data needed by first fine-tuning your model using lower quality or less relevant data. Here are 3 examples of this approach. Self-supervised. Supervised. You want to fine-tune a model to answer legal questions. Your question, answer, set is small, but you have many legal documents. You can first fine-tune your model on legal documents in a self-supervised manner, then further fine-tune the model on question, answer, pairs. Less relevant data. Relevant data. You want to fine-tune a model to classify sentiments for product reviews, but you have little product sentiment data and much more tweet sentiment data. You can first fine-tune your model to classify tweet sentiments, then further fine-tune it to classify product sentiments. Synthetic data. Real data. You want to fine-tune a model to predict medical conditions from medical reports. Due to the sensitive nature of this task, your data is limited. You can use AI models to synthesize a large amount of data to fine-tune your model first, then further fine-tune it on your real data. This approach is harder to get right, as you'll have to do 2 distinct fine-tuning jobs while coordinating the transitioning between them. If you don't know what you're doing, you might end up using more compute just to produce a model worse than what you would have gotten by just fine-tuning with high-quality data. 6. Experimenting with a small dataset can help you estimate how much more data you'll need. You can fine-tune a model on subsets of your current dataset, e.g., 25%, 50%, 100%, and plot how performance scales with dataset size. A steep performance gain slope with increasing dataset size means that you can expect significant performance improvement by doubling your data. A plateau slope means that doubling your data will give only a small improvement. Figure 8.3 shows an example of this plot. Data curation, 375. Figure 8.3. The performance gain curve with different dataset sizes can help you estimate the impact of additional training examples on your model's performance. The performance gain curve shown in Figure 8.3 is fairly typical. In most cases, additional training examples yield diminishing returns. The same number of examples typically gives a lower performance boost as the dataset grows. For example, the first 1,000 examples might improve a model's accuracy by 10 percentage points, but the next 1,000 examples might only improve it by 5. While a larger number of fine-tuning examples generally improves a model's performance, the diversity of the examples matters, too. The paper, Scaling Instruction Fine-Tuned Language Models, Chung et al., 2022, shows that model performance increased significantly when the number of fine-tuning tasks increased from 9 to 282. Beyond 282 tasks, the performance gains started to plateau, though there were still positive but incremental improvements up to 1,836 tasks, as shown in Figure 8.4. This suggests that the model benefits greatly from exposure to a diverse set of tasks during fine-tuning. The diversity of data can be reflected in task types, such as summarization and case tie-in answering, topic diversity, such as fashion, finance, and technology, and the expected output formats, such as JSON outputs or yes or no answers. 376, Chapter 8, Dataset Engineering. Figure 8.4. Diversity in fine-tuning number, measured by the number of tasks, can impact model performance. Image from Scaling Instruction Fine-Tuned Language Models, Chung et al., 2022. The image is licensed under CC by 4.0. How much data to use for fine-tuning is determined not just by what you need but also by what you can afford. If you budget $10,000 for data annotation and each example costs $2 to annotate, you can have at most 5,000 examples. You might also need to balance the budget for data and compute. Spending more money on data leaves you less money for compute, and vice versa. Data acquisition and annotation. The goal of data acquisition is to produce a sufficiently large dataset with the quality and diversity you need, while ensuring that your data practices respect user privacy and comply with regulations. Data acquisition involves gathering data through methods such as sourcing public data, purchasing proprietary data, annotating data, and synthesizing data. There's a niche but growing field of research in data acquisition strategy, how to best acquire a dataset that meets specific requirements given a budget. The most important source of data, however, is typically data from your own application. If you can figure out a way to create a data flywheel that leverages data generated by your users to continually improve your product, you will gain a significant data curation. 377. 7. I've heard so many companies talking about data flywheels in their pitches that I'm convinced it isn't legal to start an AI startup without mentioning the data flywheel. Advantage. 7. Application data is ideal because it's perfectly relevant and aligned with your task. In other words, it matches the distribution of the data that you care about, which is incredibly hard to achieve with other data sources. User-generated data can be user content, system-generated data from user usage, or user feedback. How to design your user feedback system is discussed in Chapter 10. Before investing in creating your own data, check available datasets first. Data marketplaces are vast and offer both open source and proprietary data. If you're lucky, some of them might be exactly what you need. However, it's often a mix-and-match approach. A dataset can be developed from multiple data sources via multiple acquisition channels. For example, the process of creating an instruction response dataset might look as follows. 1. Find available datasets with the desirable characteristics. You might find one promising dataset with 10,000 examples. 2. Remove low-quality instructions. Let's say this leaves you with 9,000 examples. 3. Set aside the instructions with low-quality responses. Let's say you find 3,000 such examples. This leaves you with 6,000 examples of high-quality instructions and high-quality responses. 4. Manually write responses for the 3,000 high-quality instructions. Now your data set has a total of 9,000 high-quality examples. 5. Realizing that there's not enough data for topic X, manually create a set of 100 instruction templates about X. Use an AI model to synthesize 2,000 instructions using these 10 templates. 6. Manually annotate these 2,000 synthetic instructions. Now your dataset has a total of 11,000 examples. This is, of course, an oversimplification of the actual dataset curation process, with the vast majority of steps hidden to conserve paper and save readers from tedium. For example, there might be several steps in which you realize that many of the annotations aren't helpful, so you have to update the annotation guidelines and re-annotate your data. Worse, you might find that some of them are factually incorrect, so you have to hire another set of annotators to fact-check your original annotations. Or you might find that having 100 synthetic instructions per template hurts your data's diversity, so you have to create more templates and generate fewer instructions per template. And so on. 378 Chapter 8 Dataset Engineering. Resources for publicly available datasets. Here are a few resources where you can look for publicly available datasets. While you should take advantage of available data, you should never fully trust it. Data needs to be thoroughly inspected and validated. Always check a dataset's license before using it. Try your best to understand where the data comes from. Even if a dataset has a license that allows commercial use, it's possible that part of it comes from a source that doesn't. 1. Hugging Face and Kaggle each host hundreds of thousands of datasets. 2. Google has a wonderful and underrated dataset search. 3. Governments are often great providers of open data. Data. Gov hosts hundreds of thousands of datasets, and data. Gov.in hosts tens of thousands. 4. University of Michigan's Institute for Social Research ICPSR has data from tens of thousands of social studies. 5. UC Irvine's Machine Learning Repository and OpenML are two older dataset repositories, each hosting several thousand datasets. 6. The Open Data Network lets you search among tens of thousands of datasets. 7. Cloud service providers often host a small collection of open datasets. The most notable one is AWS Open Data. 8. ML frameworks often have small pre-built datasets that you can load while using the framework, such as TensorFlow datasets. 9. Some evaluation harness tools host evaluation benchmark datasets that are sufficiently large for PEFT fine-tuning. For example, Aluther AI's LM evaluation harness hosts 400-plus benchmark datasets, averaging 2,000+ examples per dataset. 10. The Stanford Large Network Dataset Collection is a great repository for graph datasets. Often, you might need to annotate your own data for fine-tuning. Annotation is challenging not just because of the annotation process but also due to the complexity of creating clear annotation guidelines. For example, you need to explicitly state what a good response looks like, and what makes it good. Can a response be correct but unhelpful? What's the difference between responses that deserve a score of 3 and 4? Annotation guidelines are needed for both manual and AI-powered annotations. Data curation, 379. 8. My book, Designing Machine Learning Systems, discusses data augmentation in Chapter 4. Some teams, including LinkedIn, have reported that annotation guidelines were among the most challenging parts of their AI engineering pipeline. It's alarming how often people abandon careful annotation halfway due to the time and effort required, hoping instead that their models will figure out the right responses on their own. Many models are strong enough that they can occasionally succeed, but relying on models to figure that out might be too risky for many applications. The good news is that these guidelines are the same as those for evaluation data, as discussed in Chapter 4. This is another argument for why you should invest more time in curating evaluation guidelines and data. If you're lucky, your evaluation examples can be augmented or used as seed examples to synthesize new data. In the next section we'll discuss how to do so. Data augmentation and synthesis together with compute and talent. Data is the hardest challenge of AI. It's been a long-term goal of the whole industry to be able to generate data programmatically. Two processes commonly used are data augmentation and data synthesis. Data augmentation creates new data from existing data, which is real. For example, given a real image of a cat, you can flip it to create a new image of the same cat. 8. Data synthesis generates data to mimic the properties of real data. For example, you can simulate how a mouse moves through a web page to generate data for what bot movements would look like. In other words, augmented data is derived from real data, whereas synthetic data isn't real. However, since the goal of both augmentation and synthesis is to automate data creation, sometimes the two terms are used interchangeably. In this chapter, I'll often use data synthesis to refer to both. Artificially generated data has a long history in software engineering. It was originally used to generate fake data for testing purposes. For example, libraries like Faker and Chance let you generate data in simple formats such as names, addresses, phone numbers, and email addresses for testing. Let's say you've built a program to parse shipping addresses. You can use fake data generators to generate addresses in different countries and states with different formats to make sure your program can parse all of them. With AI being capable of generating data indistinguishable from that generated by humans, it's possible to synthesize much more sophisticated data, such as Doctors 380 Chapter 8, Dataset Engineering. Notes, contracts, financial statements, product descriptions, images, video commerce files, etc. This makes it easier to generate data and enables more synthetic data use cases. While synthetic data promises to significantly reduce the pressure for human-generated data, synthetic data doesn't completely replace human data. In many use cases, as discussed in Limitations to AI-generated data on page 393, mixing human and AI-generated data often produces the best value. Why data synthesis? Synthetic data is appealing for many reasons. You can synthesize data to improve the golden data trio: quantity, coverage, and quality. You can also synthesize data to mitigate privacy concerns and distill models. To increase data quantity, the biggest reason for data synthesis is that it allows you to produce data at scale, promising an abundant supply of data for training and testing AI models. More data, in theory, helps models generalize to a wider range of tasks. This is especially helpful where real-world data is scarce or difficult to obtain, such as data for rare weather conditions, data for deep-sea exploration, or data involving accidents for self-driving cars. To increase data coverage, you can generate data with targeted characteristics to improve model performance or to get a model to express specific behaviors. For example, you can generate very short texts or very long texts. You can create conversations that contain toxic phrases for a toxic detection model. Vice versa, if real-world data is toxic, you can synthesize safe data. It's especially common to use AI to synthesize adversarial examples. It's also possible to generate data for the rare class to address the challenges of class imbalance. As described in True Teacher, Geckman et al. 2022, used LLMs to generate factually inconsistent summaries that they then used to train models to detect factual inconsistency. In their paper, Discovering Language Model Behaviors with Model-Written Evaluations, Perez et al. 2022, Anthropic discussed various data synthesis techniques to generate specific datasets that can test 154 different AI behaviors, including personality traits, political views, ethical stances, and social biases. They found that in head-to-head comparisons between LM, language model, generated and human-generated datasets, LM-written datasets approach the quality of human-written ones, sometimes even exceeding them. In other words, you can use synthetic data to increase data coverage, generate targeted data to cover the areas where existing data is insufficient. Data augmentation and synthesis 381. 9. One obvious example that I didn't include in the main text is when you want to train a model to detect AI-generated content. You need AI-generated content as training examples. To increase data quality, even though the common perception is that synthetic data is often of lower quality than human-generated data, sometimes, the reverse can be true. Sometimes, humans might have fundamental limitations that cause human-generated data to be of lower quality than AI-generated data. One example is tool use data discussed earlier. Humans and AI have fundamentally different modes of operations and tool preferences. Another example is in generating complex math problems. AI can generate questions that are far more complex than what an average human expert might conceive. 9. Some teams also prefer using AI to generate preference data. While each individual human can be somewhat consistent in their preference, performance across different people tends to vary significantly, influenced not only by each person's preference but also by mood and motivations. AI-generated preference ratings, in contrast, can be far more consistent and reliable. To mitigate privacy concerns, synthetic data is often the only option for use cases where you can't use human-generated data due to privacy concerns. For instance, in healthcare, where legislation makes it hard, if not impossible, to use real patient records to train a model, you can generate synthetic patient records that do not contain any sensitive information. In insurance, you can use synthetic claims instead of using real claims that include sensitive personal and financial information. To distill models, sometimes, you might want to train a model to imitate the behavior of another model. The goal is often to create a cheaper and/or faster model, the distilled model, with performance comparable to that of the original model. This is done by training the distilled model using data generated by the original model. These are just 5 of the many reasons why people turn to data synthesis. Because of its undeniable appeal, more models are being trained with synthetic data and more techniques are being developed to synthesize data. 382, Chapter 8, Dataset Engineering. 10. Many awesome games are possible only because of procedural generation. Games like Minecraft and No Man's Sky use noise functions and fractal algorithms to create vast, immersive worlds. In Dungeons & Dragons, procedural generation can be used to create random dungeons, quests, and encounters, making the game more appealing by adding an element of unpredictability and endless possibilities. Traditional data synthesis techniques. Data synthesis isn't unique to AI. It has a long history in software testing, gaming, and robotics. Using algorithms to generate data is also called procedural generation, as opposed to manual generation. Procedural generation is commonly used in GAM-ing to generate content such as levels, maps, items, and characters on the fly. 10. Most data generation techniques used in these industries can be applied to AI. Traditionally, 2 approaches for data synthesis and augmentation have been rule-based and simulation. A newer method made possible by advanced AI models is using AI itself to synthesize data. This section gives a quick overview of these two traditional techniques before moving on to AI-powered data synthesis in the next section. Rule-based data synthesis. The simplest way to generate data is to use predefined rules and templates. For example, to create a credit card transaction, start with a transaction template and use a random generator like Faker to populate each field in this template. An example of a transaction template. Transaction ID, unique identifier, date, mm/dd/yyyy, time, HHMMSS, amount, transaction amount, merchant name, merchant/store name, merchant category, category code, location, city, state, country, payment method, credit card/debit card, cash, online payment, transaction status, completed, pending, failed, description, transaction description. Due to the sensitivity of transaction data, many fraud detection models are first trained on synthetic transaction data generated from templates like this to prove their feasibility before being given access to real data. Data augmentation and synthesis. 383. It's common to use templates to generate documents that follow a specific structure, such as invoices, resumes, tax forms, bank statements, event agendas, product catalogs, contracts, configuration files, etc. Templates can also be used to generate data that follows a certain grammar and syntax, such as regular expressions and math equations. You can use templates to generate math equations for AI models to solve. DeepMind trained an Olympiad-level geometry model, alpha geometry, using 100 million synthetic examples. Trin et al., 2024. You can procedurally generate new data from existing data by applying simple transformations. For images, you can randomly rotate, crop, scale, or erase part of an image. A flipped image of a cat should still be a cat. A slightly cropped image of a soccer game should still be a soccer game. Krashevsky et al. 2012 demonstrated in their legendary AlexNet paper the usefulness of this technique by using it to augment the ImageNet dataset. Deng et al. 2009. For texts, you can randomly replace a word with a similar word, assuming that this replacement wouldn't change the meaning or the sentiment of the sentence. For example, the original sentence, "She's a fantastic nurse," can generate a new example, "She's a great nurse." This approach can be used to mitigate potential biases in your data. If you're concerned that there's a gender bias in your data, where, for example, the word nurse is associated with women while the word doctor is associated with men, you can replace typically gendered words with their opposites, such as she with he, as shown in Table 8.2. Table 8.2. Data augmentation can help mitigate certain biases in your data. Original data, augmented data. She's a fantastic nurse. He is a fantastic nurse. She's a fantastic doctor. The CEO of the firm, Mr. Alex Wang. The CEO of the firm, Ms. Alexa Wang. Today, my mom made a casserole for dinner. Today, my dad made a casserole for dinner. Emily has always loved the violin. Muhammad has always loved the violin. Similar words can be found either with a dictionary of synonymous words or by find ing words whose embeddings are close to each other in a word embedding space. You can go beyond simple word replacement by asking AI to rephrase or translate an example, as we'll discuss later. 384, Chapter 8, Dataset Engineering. One interesting transformation is perturbation, adding noise to existing data to generate new data. Initially, researchers discovered that perturbing a data sample slightly can trick models into misclassifying it. For example, adding white noise to a picture of a ship can cause the model to misclassify it as a car. The paper One Pixel Attack for Fooling Deep Neural Networks, Su et al., 2017, showed that 97% of the not-RAL images in the Kaggle Safar 10 test dataset and 4% of the ImageNet test images could be misclassified by changing just one pixel. This poses a serious risk if exploited. An attacker could trick an AI model into misidentifying them as an authorized employee or make a self-driving car mistake a divider for a lane, leading to accidents. You can train your model on perturbed data. Perturbation can both improve the model's performance and make it more robust against attacks. See Goodfellow et al., 2013 and Masavides Foley et al., 2015. In 2019, Hendricks and Dieterich created ImageNet-C and ImageNet-P by applying 15 common visual corruptions, such as changing brightness, adding snow, changing contrast, and adding noises to ImageNet images. Perturbation can also be used for texts. For example, to train BERT, the authors replaced 1.5% of the tokens with random words, Devlin et al., 2018. They found this perturbation led to a small performance boost. Visual data can be augmented using more sophisticated algorithms. Snap, 2022, has a great case study on how they augment their assets to create unrepresented corner cases and mitigate implicit biases in their data. Given a character, they synthesize similar characters but with different skin colors, body types, hairstyles, clothes, and even facial expressions. These augmented assets are then used to train AI models. Simulation. Instead of running experiments to collect data in the real world, where it can be expensive and dangerous, you can simulate these experiments virtually. For example, to test how a self-driving car reacts when encountering a horse on the highway, it'd be dangerous to release an actual horse on the highway. Instead, you simulate this situation in a virtual environment. Examples of self-driving simulation engines include Carla, Dosovitsky et al., 2017, Waymo Simulation City, and Tesla's simulation of San Francisco. Data augmentation and synthesis. 385. Similarly, it's very common to simulate training data for robotics in a virtual environment. Let's say you want to train a robot to pour coffee, but you don't know exactly how each joint should move to make the action successful. You can simulate multiple scenarios with different joint movements and use only the scenarios where coffee is successfully poured to train the robot. Simulations allow you to run multiple experiments with minimal costs while avoid accidents and physical damage. A robot that works in simulations might not work in the real world, but if it fails in simulations, it'll likely fail in the real world. No matter how sophisticated your simulations are, however, they are simplifications of the real world. Sim2Real is a subfield that focuses on adapting algorithms that have been trained in simulations to the real world. Simulations are common to generate data to teach models to use tools. As mentioned earlier, human-generated actions might not always be the most efficient for AI agents. Simulations might help uncover actions that humans overlook. Given a query, you can simulate different action sequences, execute these sequences, and validate their outcomes. The most efficient action sequence is then used as the annotated response for the query. Simulations are particularly valuable for generating data for rare events. For example, in finance, researchers can simulate scenarios such as a company successfully going public or a significant bankruptcy to understand their market impacts. Manufacturers can simulate defects in materials or assemblies to generate data to train anomaly detection and quality control models. Similarly, by simulating the Earth's systems, climate scientists can create variations in temperature changes, precipitation patterns, and extreme weather scenarios. This synthetic data is then fed into AI models, enabling them to learn from a broader spectrum of possible futures. Both rule-based and simulation-based techniques have been useful for many use cases, but it wasn't until AI became capable of generating realistic and high-quality data that data synthesis really took off. Let's look into those methods next. AI-powered data synthesis. Just as there are virtually infinite ways for humans to generate data, AI can also do so in many ways. The techniques discussed here are not comprehensive, but they should give you a good overview. Powerful AI models open many new possibilities for simulations. AI can simulate the outcomes of arbitrary programs. For example, Stable Toolbench, Gua et al., 2024, demonstrates how to use AI to simulate APIs without having to evoke them. Imagine you want to train a model to interact with a set of APIs. Instead of making actual API calls, which might be costly or slow, you can use an AI model to simulate the expected outcomes of those calls. 386, Chapter 8, Dataset Engineering. AI can simulate humans. For example, imagine you want to train a bot to play chess. A game played by humans might take too long. Matches with AI players would be much faster. To train its Dota 2 bot, OpenAI used a simulator that enabled the bot to play approximately 180 years worth of games every day. The bot